In this video here, we're going to take a look at the Euclidean algorithm. So before we start then with the Euclidean algorithm here, let's just quickly discuss common divisors as well as greatest common divisors. Now we can use the definition of divisibility to write formal definitions of common divisors as well as greatest common divisors. So in that case then, if a, b and c are integers and c is not equal to 0, then c is a common divisor of a and b if c divides a and also c divides b. And I'm hoping this definition here is pretty obvious, right? And also here, if a and b are both integers with at least one of them not equal to 0, then we can define the greatest common divisor of a and b as the largest positive integer which divides a and b. And the greatest common divisor of two integers a and b is a positive integer d that satisfies the following two conditions. So d divides a and d divides b, and also if c is a common divisor of a and b, then c must be less than or equal to d. So with all that in mind then, let's just have a quick look at the Euclidean algorithm. So the Euclidean algorithm gives us a method of quickly finding the greatest common divisor of any two integers. So how does it work? Well, if we're given positive integers a and b where a is greater than or equal to b, then for the first step here, what we do is we apply the division algorithm to a and b to find integers q1 and r1, such that a is equal to q1b plus r1, where r1 is between 0 and b. And if r1 is equal to 0 here, then b divides a, and the greatest common divisor of a and b is equal to b. Okay? At that point there, the Euclidean algorithm would be complete. Okay? What you'll often find here, especially with exam questions, is that is never the case, right? We do have to do at least a few steps of the Euclidean algorithm. So, if r1 here, our first remainder, is not equal to 0, what we do then is we apply the division algorithm to b and r1 to find integers q2 and r2, such that b is equal to q2 r1 plus r2, where r2 is between 0 and r1. Now, again, if r2 here, the second remainder, is equal to 0, then in that case, the greatest common divisor of a and b is equal to r1, our first remainder. Okay? And again, if the second remainder here, r2, is not equal to 0, we must continue with the process and the algorithm. Okay? And what this does then is this results in the following system of equations. So as you can see here then, a is equal to q1b plus r1. That's what we started off with here, right? Moving on then, we get b is equal to q2 r1 plus r2. Moving on, we get r1 is equal to q3 r2 plus r3, so on and so on. You can see what happens here, right? So for the final step then, as you can see here, we get a remainder of 0. And the Euclidean algorithm here terminates once we reach a remainder of 0, okay? And in that case then, the last non-zero remainder, Rn here, that's this remainder here. Just put a box around this here. So Rn then, this is the greatest common divisor of a and b, okay? The two numbers that we started with, right? Our two positive integers. Now, I do think here, once you kind of read it out like this, the Euclidean algorithm sounds a lot more complicated than it actually is. In practice, the Euclidean algorithm is pretty straightforward, okay? It's an iterative process, and we just keep repeating this process here until we reach a remainder of 0, okay? Now, I think the best way to really demonstrate here the Euclidean algorithm is to just work through a couple of practice questions here, okay? So that concludes this introduction here to the Euclidean algorithm. Let's just work through then 2 practice questions. Let's just make a start here then with question 1. Now, as we can see then for question 1 here, pretty straightforward. All we want to do then is use the Euclidean algorithm to find the greatest common divisor, the GCD of 108 and 320. So to begin with here then, we start with the bigger of the two numbers here, or the larger of the two numbers, which in this case is 320, right? So we have 320 is equal to, so we now take the remaining number here, 108. So we have 108 here, okay? And what we now consider then is how many times does 108 go into 320, right? Well, this will go in 2 times, so we do 108 times 2. So 108 times 2. And what we also need to consider here then is what is the remainder. So 320 minus 108 times 2, that gives us 104. So our remainder here then is 104, right? So hopefully this first step here was pretty straightforward. This is just simply the division algorithm, right? What we covered in the previous video. Now at this point here then, we can clearly see that our remainder here is not 0, right? We've got 104. So what that means then is we need to continue with this process here, right? The algorithm will not terminate at this point. Now for the next step here, what we now do is just shift everything along. So the 108 here goes on the left-hand side. So I get 108 here on the left-hand side. And this then is equal to, so the 104 here, that shifts along and basically just takes the place then of the 108 in the previous line. So we get 104. So again, all I do here then is I consider how many times does 104 go into 108? Well, nice and straightforward then. It just goes in one time with a remainder of 4. We do 104 times 1 because it goes in one time. And we get a remainder of 4. Okay? Again, we can see here that our remainder is not 0. So we need to continue then with this process here. Okay? And again, all that happens then is everything just shifts along. So the 104 here moves on to the left-hand side. So we get 104 is equal to, so the 4 here then shifts along. So we get 4 then. Well, how many times does 4 go into 104? Well, 4 goes in 26 times perfectly. We get left with no remainder here. So I've got 4 times 26. As we've just said, right, we get no remainder here. So plus 0. And once we obtain a remainder of 0 here, at this point now, the algorithm will terminate. Okay? So what that means here then, and let me just quickly do this in a different color here, is the last non-zero remainder then, this value here 4, this is the greatest common divisor of 108 and 320. Okay? So therefore then, let me just write underneath here, the greatest common divisor, or GCD here, of 108 and 320 is equal to this value here, the last non-zero remainder, which in this case gives us 4. Okay? And there we have it then. So hopefully nice and straightforward. That gives us the solution to question 1. So just moving on to the last question here then, where we have question 2. Now for question 2 then, again, pretty straightforward here. All we want to do then is use the Euclidean algorithm to show that 35 and 52 are coprime. Now, I didn't mention it in the introduction of this video here. I do mention it in the next video, which obviously isn't helpful if you do in this video. But this definition here, or the definition of this word coprime, you might already be familiar with it, but all this means here then is the GCD of these two numbers then. So what we want to show then is the GCD of 35 and 52 here is equal to 1. Okay? So to do that then, all we're going to do here is use the Euclidean algorithm. So again, all we do here is we start with the larger of these two numbers. So 52 then is equal to, so my remaining number here then is 35. So I've got 35. Well, how many times does 35 go into 52? Well, clearly that's just 1. So 35 times 1, like so. And what's our remainder here? Well, our remainder in that case is 17. Okay, so we get plus 17 there. Now, clearly our remainder here isn't 0, so we need to continue with the algorithm and the process. So again, all that happens here is everything shifts along. So the 35 here will go on the left-hand side. So we get 35 is equal to, so the 17 here then shifts along. So I get 17. Well, how many times does 17 go into 35? Well, it goes in 2 times. So I get 17 times 2 here. What's our remainder then? Well, that's just simply 1, right? Because 17 times 2 is 34. So we get plus 1 there. Okay, hopefully nice and straightforward, right? You know, these steps as we go along, right, are just simply an application of the division algorithm. Again, I can see here that my remainder isn't 0. So all that tells us here then is we need to continue. And again, all we do, right, is we just shift everything along. We get 17 is equal to, So the 1 here shifts along. So I get 1. Well, how many times does 1 go into 17? Well, clearly that's just 17. So we get 1 times 17 here. And obviously then we get left with a remainder of 0. Okay? And again, once we reach a remainder of 0 here, all that tells us then is the algorithm is complete, right? So at this point here, our remainder now is the last non-zero remainder. And therefore, in that case, then the GCD of 35 and 52 here is equal to 1, which is exactly what we wanted to show, right? So therefore, then 35 and 52 are coprime. Okay, and there we have it. Perfect, right? That gives us the solution then to the very last question, question 2. And that brings the end then of this video here on the Euclidean algorithm.